Alright, now it's time to discuss mechanical waves. Part 1, properties of waves. So a couple of things we need to discuss first. There's several main topics we're going to go through. Parts of longitudinal and transverse waves, the equations related to them. We're going to discuss wave properties and speed. We're going to discuss how waves interfere with each other and interact with each other. We're going to discuss what happens when waves get to a boundary. We're going to discuss the Doppler effect and beats. Alright, so to start off with, there are two main types of waves. You can have a transverse wave or a longitudinal wave. And a transverse wave, that's the wave you kind of think of. The wave you see at an ocean, the wave you do at a ball field. It's where the disturbance is perpendicular. And if you look at my mouse, you notice how an up and down wave, even though the energy is traveling this way. So the disturbance is perpendicular to the direction that the energy is traveling, where in a longitudinal wave, the disturbance is back and forth, so that's caused by pushing it this way as the wave travels this way. So parallel versus perpendicular is the definition, but looking at those two types of waves, you can see it immediately. Alright, so we're going to start by discussing transverse waves, and there are a couple of things to look at. We need to discuss some vocabulary. Number one, the wavelength is the distance between two waves. Well, how do you define a wave? And that's where I'm going to come down here. We have two crests, and the crest is the top of the wave. That's why Crest toothpaste, they talk about the white caps of the waves, because that's where the crest of a wave is. And then you have troughs, just like pigs eat out of, that's the bottom of a wave. You have your equilibrium point, that's right in the middle. And I want to give you guys kind of a heads up, in case you see a graph in the future, they don't always draw the waves so the equilibrium point is where the x-axis on the graph is, but the equilibrium point is always halfway between the crest and the trough. It's always right there in the middle. And then the amplitude, that's the height of the wave. And it could be from the equilibrium point to the crest, or it could be from the equilibrium point to the trough. And node and antinode, we'll get a little bit more in depth on those when we get to waves on a string. But wavelength is the length of one wave. So it could be from crest to crest, or it could be from trough to trough, or it could be from equilibrium point to two equilibrium points apart. Because a full wave is a full sine curve. So you have to complete a full sine curve or a full cosine curve. So now we need to discuss period. That's the amount of time for one full wave to pass. So if start 1 Mississippi, 2 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi. So that wave has a period of 5 seconds. The amount of time for one full wave to pass from crest to crest, trough to trough, or double equilibrium point. Frequency is just the inverse of that. Remember, frequency is cycles per second, where period is seconds per full cycle. So they're complete inverses of each other, just like we learned in the last section. The other thing I want to point out is notice this red dot. If you pick any point on a wave, that point just oscillates up and down. It doesn't move left and right at all. If I leave my mouse pointer there, you can see the red dot keeps going up and down at the same exact point every single oscillation. So it's not moving up and down, it's just this vertical energy moves the dot up through the wave and the dot stays there. So as the wave passes through, the dot travels up the wave and down the wave. Just like you do if you're in an ocean wave, it lifts you up and it drops you right back down. And also, recall that waves are created by vibrations or oscillations. So if you look at the left side, this red block is oscillating up and down, and every time it oscillates, it creates this energy in this case, a string that's traveling from left to right. And the amount of times it goes up and down per second is the frequency. So the frequency of a wave is only dependent on the source of a wave. So the number of times it oscillates up and down per second is the frequency of the wave. So now let's get a little bit more into this and discuss wave speed. Remember that wave frequency depends only on the source, just like we were just discussing. So how many waves pass in a second? Well, this is not even one full wave per second, so it might be 0.2 waves per second, because remember our period was 5 seconds, so the frequency would be 1/5, or 0.2 hertz, 1/5 of a wave per second. The speed that the wave travels depends on the medium. Medium is fancy for the material that a wave travels through, and we'll discuss an equation to calculate the speed in a string later. But waves are going to travel at different speeds, whether they're traveling through air, through water, through wood, through steel. It depends on the compactness of the atoms and the density of the atoms. So a rough thought is the more closely packed the atoms are together, the molecules are together, the less time they have to go to bump into the next particle. So if you have particles all right next to each other, one wave is going to pass right through them. But if they're spread out, it's going to take time for the wave to travel from particle to particle. So the more spread out the atoms are, the slower the wave is going to travel. So more compact particles, like a solid, will actually send sound through faster than spread out particles. Gases have a slower velocity than solids for waves traveling through them. And combining those two thoughts, even if a wave travels into a new medium, let's say it goes from a gas into a solid, so my sound waves coming from my vocal cords travel through the air molecules, boom, and it gets to this new medium, this solid. When it travels into the medium, it will maintain the same frequency. That's a really important concept. So this frequency will still be the same even when it travels from one medium into the next. So even if it slows down or speeds up, just like I said before, if it travels from a gas to a solid, it's going to speed up. So it's going to speed up but maintain the same frequency, and the wavelength will, higher velocity, same frequency, it will have a bigger wavelength to compensate for it. So the same number of waves still pass the same point per second. So to compensate for this, the wavelength will increase or decrease directly with the speed. And there's an equation that shows that if you increase velocity, wavelength will have to increase with it if the frequency maintains constantness. All right, so here's all the equations you need for this unit. This unit's a little bit special in that there's a couple of equations that you need to know but aren't provided on your equation sheet. So you're going to have to put in a little bit of time. I would get a 3x5 card and write the equations down on it. And I will go through each of these equations one by one. There's no equation on this page that doesn't show up later in the unit or later in these notes, but I'm going to present them to you now. So all of the equations that are provided to you are velocity equals frequency times wavelength. That's it. That's the only equation on the equation sheet. So now the equations that are not provided but are expected for you to know consist of all of these. And it looks like a lot, but again, there's really only 3 equations there, with a slight technicality of a 4th. And we will go through each one. This one discusses how the speed in a string is related to the tension in the string and the density of the string, which collapses into one equation. This one discusses the Doppler effect, and this one discusses beats. And again, we'll discuss each one of these in depth as we go through, so I don't want to take too much time right now and discuss them now. The first equation, and I'm going to immediately start discussing it in terms of v equals f lambda, because I like when equations are straight across the line. You can see what's happening. You don't have to think about fractions. It's super straightforward. So the speed of a wave equals the frequency times the wavelength. the length of one wave, frequency, number of oscillations per second, and speed, how quickly the wave is traveling. So now we're going to discuss the two different types. Oh, now we've discussed transverse waves. I think we discussed them. We're going to discuss longitudinal waves. And one thing I think I should point out is light travels as a transverse wave and sound waves travel as longitudinal waves. So I speak, it bumps an air molecule, which bumps the next air molecule, which bumps the next air molecule, and so on and so forth. But when you do that, sometimes the air molecules are closer together. And other times that's going to bump this air molecule out and they're going to bounce off of each other, and that's going to create a gap. So you're going to have these packed together areas and these gaps. Packed, gap, packed, gap. Or, in physics terms, compressions and rarefactions. Where a compression is any area where it's densely packed, and rarefaction is anywhere where they're spread out. And sound waves are the most common types of longitudinal waves. This is like when you take a slinky and you push it forward. We've already discussed compressions and rarefactions. But the question is, how would you find the wavelength or period and frequency? Because remember, if you have the period, you automatically know the frequency. If you know the frequency, you automatically know the period. Period is 1 over frequency. Frequency is 1 over period. So if you have one, you have both of them. But how would you find the wavelength? What would the wavelength look like on this longitudinal wave up here? Well, the wavelength is just distance between successive compressions or successive rarefactions. So this is a sound wave traveling through the air, and they've translated it to a longitudinal wave, or excuse me, a transverse wave down below, so you can see what it would look like. And these compressions are where the air is packed together more, or you have max pressure, and the rarefactions are where the air is less packed together, so you have minimum pressure. High pressure, low pressure, high pressure, low pressure, high pressure. It's kind of trippy to look at. I love it. So how would you find the period? Well, I'm going to start my stopwatch, and the period is going to be the amount of time for one full wave. So looking at the compression, start, 2 Mississippi, 3 Mississippi, 4 Mississippi, stop. 4 seconds for compression to compression. It would also be 4 seconds from rarefaction to rarefaction. So compression to compression, rarefaction to rarefaction, I don't care what you choose. Just like before, you could have done crest to crest or trough to trough. Those are the easiest ways to measure it. So some real life questions that often come up in this unit. Helium, right? Wait a minute, I thought you said frequency only depends on the source, which I did say. The amount of times my vocal cords are vibrating is the frequency. So I can vibrate my vocal cords very, very quickly, or I can vibrate them a little bit more slowly. So it would seem that your vocal cords the frequency is being changed by the helium. But what's actually going on is your vocal cords will vibrate a little bit more quickly or a little bit more slowly. And that's actually because of the density of helium, or the mass of helium. Think about shaking a small box versus a heavy box. If you try to shake a heavy box, it's going to be really, really hard to shake, which means you are only going to be able to hit it so many times per second, or shake it back and forth so many times per second. But with a light box, you can shake it all you want, and you can move much more quickly. And your vocal cords are the same. Your vocal cords will actually slow down or speed up based on how quickly they hit the light helium, the less dense helium. So it's not that they're changing the frequency of the air, or of the wave in the air. They're changing how quickly your vocal cords can vibrate back and forth. So now your vocal cords are vibrating back and forth much more quickly, which creates a higher frequency. And the correct word for this is timbre, Timbre. And we're not going to go too much more in depth with that, but I think that's always a fun question. I wish I had some helium. I hope there's helium for generations to come. I'm not banking on it. Another common question is, or actually a question I have for you is, does sound travel faster or slower at higher altitudes? Take a minute and think about it. pause if you need to because I'm going to jump right into it. At a higher altitude, the pressure is lower and the air molecules are fewer and farther between because air is kind of like blankets. So you stack these blankets on top of each other. So the higher altitude you are, the less pressure you have on you. But as you go further and further down, just like swimming to the deep end of a pool, you have more blankets stacked on top of you, which means the air molecules are all packed together. So then as you go higher and higher up, there's less blankets packing everything together, so things are more spread out. And remember, if they're more spread out, it's going to take more time for an air molecule to bump into the next air molecule. So the higher altitude you are, the slower the velocity will be. And that's just the same explanation that I just said, but in words for those of you visual people. All right. So the second wave's equation we need to discuss allows us to calculate the speed of a wave on a string that's being pulled with tension T. So this string is being pulled with tension T by this mass M, and tension is equal to mass times gravity because this box is in equilibrium. So the weight or force of gravity has to equal the force of tension. T equals mg. But that doesn't really matter. We only care about the tension in the string because the speed that a wave will travel through this string depends on how tightly it's pulled, which makes sense because you can change the speed. If you pull a string really, really quickly, a wave is going to shoot right down it. But if it's slack, the wave is going to take its time getting down there. The other thing it depends on is the linear density of a string. So a string that's really, really heavy is going to take more, it's going to take more time for the wave to travel through versus if you have a light string, it's going to shoot right through it, like cracking a whip. Those are always really light strings, and the wave can shoot right down the string, especially the tip of the string, which is where you want the most speed so it can crack the sound barrier. And the equation for that, to calculate the speed in a string, is the speed is equal to the square root of the tension over the linear density of the string, where the linear density of the string is just how much mass divided in how long it is. That's what density is, right? How packed together the mass is. So the mass over length is the linear density. So we can combine these two equations to find a total equation for velocity, where velocity is the square root of tension over mass over length, or over linear density, just like we have up here. It's the same equation combined with this one. So what would happen to the following using that equation we have before? And I'll put it back up there for 1 second in case you need it, although you have rewind features, so what the hell does that matter? What would happen in the following situation? If in the same situation the tension were increased, so we had a speed in the string, but now we've increased the tension, would the velocity increase, decrease, or remain the same? Well, the velocity would increase, right? Because as we saw in the equation, tension is in the numerator, so if you increase the numerator, you're going to increase the entire right side of the equation. So more tension is going to increase the right side of the equation, which is going to increase the left side of the equation. So the more taut it is, the faster the wave is going to travel. What if we change the frequency? So this wave is created by something oscillating on this side of the string, the left side of the string. So it's vibrating. So what if you vibrated it faster? How would that change how long it would take the wave to travel down the length of the string? I'm hoping you're paying attention because the answer is it wouldn't. The frequency depends on one and only one thing: how quickly the source is vibrating. Even if it travels into a new medium, the frequency stays the same. The frequency is dependent only on the source of the vibration. In this case, how quickly my vocal cords are vibrating back and forth. Again, how quickly my vocal cords are vibrating back and forth. Slower versus faster. Okay, how would the wavelength change? Oh no, I'm sorry. Let me rephrase. If we Wait, that question doesn't make sense. Oh, that's what I was asking. Okay, so if we increase the velocity, or excuse me, increase the tension, how would that affect the wavelength? Well, remember, velocity is frequency times wavelength. So increasing the tension increased the velocity. And because v equals f lambda, if velocity increases and frequency has to remain the same, then the wavelength has to increase to compensate for it. So bigger velocity is going to make a bigger wavelength, assuming the frequency stays constant, which in this situation it does. So now we need to discuss what happens when two waves interact with each other, or overlap with each other. So in this graph above, we have a green wave traveling to the right, we have a red wave traveling to the left, and the blue wave is what you would actually see. The blue wave represents what the wave looks like. So where you have two crests overlapping, red and green, you get a really big crest. So let's watch when they're overlapping now, you get a really big crest. And if we have two troughs overlapping, let's watch this red overlapping with the green, really big trough. But when you have a crest overlapping with a trough, like right now, you notice how it collapsed to the equilibrium point? That's constructive interference versus destructive interference. So when two waves overlap, it depends on which part of the wave is overlapping. If you have two crests together, they're going to add and make a megacrest, also known as constructive interference. If you have two troughs, they're going to make a megatrough, also constructive interference. They're adding to make a bigger wave. Whether it's a crest or a trough doesn't matter. They're still building a bigger wave. Destructive interference is when they're working against each other and they collapse. But whatever the amplitude of either wave is, so if you have a wave with 1 meter tall and a 2 meter tall wave, when they're overlapping, they're going to make a 3 meter wave. Whoops. So two crests will make a really big crest and two troughs will make a really big trough. That's constructive interference. Let's hope we get, here's two troughs overlapping. They have an amplitude of half meter, and right there, did you see they added together to make a 1 meter trough? And now we have two half-meter crests making a 1 meter crest before they pass through each other. It's important to note that the waves continue in the same direction, so this trough is going to continue traveling as a trough after they interfere. So two waves will come towards each other, overlap, interfere, and then continue passing through each other like a sailor in the night. Ships in the night. All right, standing waves. Over here, this blue one, this is a standing wave. A standing wave occurs when the wavelength perfectly fits inside a one wavelength or multiple wavelengths. So right there we have, let's see, one sine curve ends there, two sine curve ends there, and 2.5. So if you have a multiple of half wavelengths packed into a string, and we'll discuss that way more in depth in the next section, in part 2 of the notes, you create this standing wave. And that's where two overlapping waves of equal frequency make several waves that appear to stay in one position. So this red and green waves, they have the same frequency, and they make this blue wave look like it's staying in the same position. And you notice how this spot never changes from its position. This spot never changes from its position on the blue wave. This spot never changes. This spot never changes. They stay at the equilibrium point. Those are called nodes. However, this place where it turns from a trough to a crest to a trough to a crest is called an antinode. So they create nodes and antinodes. Nodes are just wherever it's always at the equilibrium position. Antinodes are, of course, where it makes crests and troughs. All right, beats. When you get waves overlapping, they aren't always going to have the exact same frequency. So up here, this red one actually has a slightly faster frequency, or slightly higher frequency. I don't know if you can tell that. And when you do that, you're going to get areas of overlap where the troughs overlap for a longer period of time. And then they get out of phase further and further and further and further and further until their crests and troughs shift over top of each other. So you get alternating periods of constructive interference and destructive interference. Constructive, destructive. And it creates this loudness and then this quietness and then this loudness and then this quietness. Because the amplitude, the only thing the amplitude affects is how loud it is. This and this have the same frequency. Assuming I can keep my frequency and my voice the same. Those of you who are tone deaf will be like, yeah, he nailed it. And those of you musicians will be like, oh my God, he's terrible. And that's okay. I'm doing my best here. I'm a physics teacher, not a musician. So if two frequencies are slightly off, they'll oscillate between constructive and destructive interference. They'll get in phase and out of phase, in phase, out, or in phase, out of phase, in phase, out of phase. And this is called beats. And if you have two musicians playing together, they'll actually use this to their advantage because they'll play two frequencies at this, or the same string on both their guitars at the same time. And if they're perfectly in phase, there will be no beats. It'll just go. But if you get slightly out of phase, it's going to go. Here, I'll show my mouse. So it's going to go. My mouse disappeared. So these, the closer they are, the longer it'll take between beats. So if you're just 1 hertz off of the other person, it's going to have a slow frequency. So 500 hertz and 501 hertz will go E. But as you get further and further away from each other, so let's say one person has their guitar string at 500 hertz and the other person has 502 hertz, now it's going to get out of phase and back in phase much faster. And it's going to go. And the equation you use to calculate this is you just subtract the two frequencies. So 500 and 501 hertz, the beat frequency is the absolute value of the difference of them, or 1 hertz. Or it's going to go in phase and out of phase once every second. With the 500 and 502 hertz, it's going to go in and out of phase twice every second. Versus 500 and 501. Alright, so we need to discuss boundaries. Boundaries are what happens when a wave on a string gets to the end of whatever you have it tied to. So let's say I tie a string to this pole and then I whip my string at it. What's going to happen when the string gets there? Well, it depends on if the string is fixed, meaning tied tightly, or it's not fixed. It's loosely wrapped around so it can slide up and down the pole. So it's either going to be wrapped tightly where it can't slide, or it's going to be wrapped loosely where it can slide up and down. And that's going to change how the wave is going to reflect. So if you have a fixed boundary in this first situation, notice how the crest turns into a trough because the energy has to go somewhere. So the energy gets pulled into that and reflected back on the opposite side. But if I whip it with a loose end, notice how the crest remains a crest. So that's fixed boundary versus unfixed boundary. Fairly straightforward, I think. All right, Doppler effect. You've seen it so many times. Not quite seen it, but you know what I mean. You're the blue spot. Did you see it? Did you notice how as the car got closer to you, and I'm going to play that again. As the car got closer to you, or as it was approaching you. You see how these waves are more spread out, and these waves are more compact, and these waves are more spread out? As a wave is, or as a sound source is approaching you, the waves are really close together. But as a sound source passes you, the waves are more spread out. Basically, a higher frequency when it's coming towards you, and a lower frequency, less waves per second, are hitting you after it passes you. This is called the Doppler effect. And this is the equation to calculate it. And we'll look at a couple of examples after we do this. But the frequency that you hear, the frequency that's observed, is equal to the frequency of the source times the speed of sound plus or minus the speed of the observer over the speed of sound plus or minus the speed of the source. And you can memorize these 4 rules down here, or you can think of it intuitively. If there's a sound coming towards me, and we know the observer is always towards the source. I'm going to say that before I restate what I was saying. The observer is on the source, or on top of the source. Just like frequency comes observer before source, observer before source. That can help you remember observers in the numerator, sources in the denominator. But whether you use a plus or minus is something you kind of have to think through. So if an observer is traveling towards the source of the sound, if I'm traveling towards the sound, is that going to mean the waves are seemingly closer together than if I were just listening? Well, yeah, because I'm bumping into the sound waves more frequently. So let's imagine there are circles of sound coming out of my source. Woo, 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 woo. Making circles. If I travel towards it, I'm going to bump into those sound waves more quickly. So if my velocity is towards, that's going to make a higher frequency. So the frequency observed is going to have to increase, which means that these are going to have to add together, because you would want a bigger numerator to create a bigger observed frequency. Now, as far as the source, whether you use plus or minus, well, we can again think of it intuitively. If a car is traveling towards me, the source of the sound, the source of the velocity, the source of the frequency, it's going to have a velocity. So if I'm standing still and now the source is traveling towards me, it's going to have a higher frequency, right? As it's traveling towards me, it has a higher frequency. So if it's traveling towards me, do we need to use plus or minus? Well, if it's traveling towards me, that would mean a higher frequency. So we need a bigger left side of the equation, which means this denominator is going to have to be smaller. So if it's traveling toward me, I subtract the velocity of the source. So you can memorize this equation, but I think you should be able to intuitively think about whether these should be positive or negative instead of memorizing these 4 situations. If you can memorize all 4 of them, kudos to you, good for you. And one last situation I want to point out is if neither the source nor the observer is moving, so this is emitting a 50 hertz frequency, well, the speed of sound, 330 plus 0, divided by 330 plus 0 is going to collapse to 330 over 330, which is 1. In that situation, the frequency of the source times 1 is going to be equal to the frequency of the observer. So you're going to hear exactly the sound that was created, which makes complete sense. If neither of us are moving towards each other or away from each other, then I'm going to hear exactly the frequency that was created. So let's look at some GIFs of how this looks. So notice this source is moving towards the observer. And as it's moving towards the observer, you see how the waves are more closely packed together, this red area, but when it's moving away from the observer, now you see how the waves, for a very brief amount of time, were further apart from each other. And the one last thing I want to point out, and I don't have a diagram of this, but if you're traveling at the speed of sound, it's going to create sound pulses, boom, 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 boom. But if you're traveling at the speed of sound, the front of all of those circles is going to completely overlap with each other. And it's going to create this giant boom, 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 boom. All of these overlapping circles of sound, which is when you break the sound barrier, the sonic boom. And this actually happens with the speed of light as well, but it's way, way, way harder to achieve, because if I am traveling at even 3 meters per second, that's going to be a 1% increase on the speed of sound, 330. Close enough. But if I'm traveling at 3 meters per second compared to the speed of light, 300 million meters per second, I'm still changing the color that you see, the frequency that you observe. But I'm changing it by a much smaller percentage, so it's harder to tell a difference. But this is, I think they call it redshift, something like that. Something about stars. If you're really into it, go look it up on your own, but that's essentially what's going on. All right, so that concludes part 1, where we discuss property of waves, mechanical waves. In the next part, we'll discuss waves on a string and waves in pipes. And to finish it up, let's finish it off with my dad joke of the day. What do you call a chicken staring at lettuce? A chicken sees a salad. I'll see you guys next time.